Welcome back, Focus Learners. This is another explainer brought to you by Forge College. Now, if you've been following along, you know we're right in the thick of your capstone module. In our previous lesson, Framing the Integration, SegWit and Taproot together, we talked about the high-level framework. But today it's time to get our hands dirty. We're going to look under the hood of Bitcoin to see exactly how these protocol upgrades interact in the wild. Okay, let's dive into our syllabus for today. First, welcome to the integration. Then, the locksmith model, followed by core technical interactions. After that, we'll measure weight and vsize, check out a real-world multi-sig showdown, and finally, wrap up with capstone takeaways and tooling.
Section 1. Welcome to the integration.
So it's time to transition from those high-level architectural theories into the concrete, everyday mechanics of how SegWit and Taproot actually communicate. What we're doing here is shifting our focus from abstract concepts to measurable operational impacts. In the last lesson, we saw that SegWit moves data to the witness, and Taproot uses key paths and script paths. But what does that actually mean for the network? Well, it changes exactly where signatures and script commitments land in a serialized transaction. It allows for incredible things like signature and script aggregation, and most importantly, for anyone actually transacting on the network anyway, it radically impacts transaction size and the fees you pay.
Section 2. The Locksmith Mental Model.
Before we get completely lost in block data and byte math, let's use a quick visual analogy to ground all this heavy technical lifting. I want you to imagine every single unspent Bitcoin, every UTXO, as a lockbox. A Taproot lockbox actually comes with two totally distinct ways to open it. On the left here, we have the script path spend. Think of this like a clunky, highly visible combination lock right on the outside of the box. If you use it, everybody can see the exact combination you dialed in. But on the right, we have the key path spend. This is Taproot's real magic trick. It's a sleek, completely hidden master keyhole. If you have the right signature, the master key, you literally just slide it in and the box opens up. No one ever even knows that clunky combination lock was an option. Now let's add SegWit to our locksmith analogy. If Taproot gives us the types of locks, well, SegWit is basically the network's shipping pricing rule for the lockbox itself. SegWit essentially says that the heavy metal on the outside of the box, the base transaction data, is super expensive to ship across the network. But the little combination slip or the master key that you tuck inside the package, the witness data, is heavily discounted. So the unlocking items inside the box ship cheaper than the heavy metal on the outside. This shipping discount is absolutely crucial. It's the key to everything that follows.
Section 3. Core technical interactions.
So how do these locks and shipping rules actually interact with transaction data? This is where the rubber meets the road. On the left, we have legacy base bytes. This is the old, heavy, expensive way of doing things. Imagine you're standing in a coffee shop line, and the guy in front of you decides to pay for a $6 latte using entirely pennies, counting them out one by one. That's a legacy transaction. It's shoving all its signatures and scripts into the base bytes. It's heavy, it clogs up the block, and the network charges an absolute premium for it. Now, look at the right, witness bytes. Light, cheap, and super efficient. Because of SegWit and optimized by Taproot, pushing this data into the witness is like the next person in line just effortlessly tapping their phone to pay.
And this gets even better because of signature aggregation. Taproot enables Schnorr signatures, which basically allow us to take multiple partial signatures, like you'd have in a multi-signature wallet, and mathematically match them together into one single compact signature. Going back to our coffee shop analogy, this isn't just tapping their phone to pay. This is you and 3 friends splitting the bill, but instead of 4 different transactions counting out change, it all gets bundled into one single smooth VIP card tap that hits the witness data perfectly.
Section 4. Measuring weight and vsize.
Okay, let's put some hard math behind our analogies. Notice that massive number 4 jumping out right here? Why is this so important? Well, because in the Bitcoin protocol's weight-based accounting, base bytes are severely penalized. A base byte weighs exactly 4 times as much as a witness byte, 4 to 1. This is the literal numeric advantage of the SegWit upgrade.
Let's walk through the exact formulas you're going to need for your capstone. First, you calculate weight. You take your base bytes, multiply them by 4, and then add your witness bytes. Notice how the witness data totally escapes that multiplier. By pushing complex spending data into the witness, you're effectively getting a 75% discount on the weight of that data. Then, to get the virtual size, or vsize, which is what your wallet actually uses to calculate fee rates, you take that total weight and divide it by 4, rounding up to the nearest whole number. That's what seal or sealing means in the formula.
Section 5. Real-world multisig showdown. Let's take all this math and test it in a concrete scenario. A standard 2 of 3 multisignature wallet. This brilliantly illustrates the climax of the integration. On the left, a legacy P2SH spend is massive because all those multisig scripts and signatures are stuck in those heavy base bytes. In the middle, SegWit nested multisig drops down to 263 vbytes because, hey, we moved the data to the discounted witness section. But look at the right side, the taproot key path spend, utilizing signature aggregation. Because it hides the script entirely and bundles the signatures into a single master key in the witness, it drops to a sleek 216 vbytes. No way, right?
So the crucial point to take away here is this. You get an 18% vsize savings using the taproot key path compared to SegWit nested. And remember, smaller vsize directly equals lower required Satoshi fees when the mempool fee rate is applied. You're quite literally paying less money for the exact same level of security, all while gaining privacy because your script wasn't even revealed. It's a real game changer.
Section 6. Capstone takeaways and tooling. Let's translate this showdown into actionable notes. For your capstone deliverable, you really need to be methodical. Here is a strict 4-step workflow. 1. Select your transaction template, legacy, SegWit, or Taproot. 2. Estimate the byte components, being very careful to separate base bytes from witness bytes. 3. Compute the weight and vsize using the exact formulas we just covered. And 4. Translate that vsize into fee estimates using a sample mempool fee rate. Seriously, do not guess here. Run the math.
But before you write down that 18% savings as a universal truth, we have to ask a quick question. What about ecosystem readiness? Just because the Bitcoin protocol supports this amazing hidden master keyhole, does that mean every wallet software actually knows how to use it yet?
Well, the reality is no. You have to ground your analysis. As our source material beautifully puts it, theoretical vsize gains are scaled by a factor representing available aggregation and wallet adoption. Basically, if the participants in a multisig don't have access to the tooling required to create that aggregated signature, they literally can't do a key path spend. You must discount your theoretical savings by an ecosystem readiness percentage, say 50% or even 0%, depending on the specific tools your theoretical users have, to make your capstone claims realistic and evidence-driven.
Which leaves us with one final thought. We've mastered the mechanics, the sizes, and the fees today. I want to thank you for joining me for this explainer, and remember to visit forge.college to review these formulas and explore tons of other Web3 topics. But as we wrap up, I want you to ask yourself, how do these hidden combination locks change network surveillance? Are you ready to analyze concrete privacy outcomes? We'll tackle exactly that in our next module.